Hello, my name is Theo, and this is magnetohydrodynamic bubble removal for water electrolysis in reduced gravity environments. Water electrolysis occurs when electrodes are submerged in a conductive fluid, like an electrolyte, and a sufficiently high voltage is applied to evolve gas on each electrode. Hydrogen on the left here, and oxygen on the right. And this is of interest for spaceflight, for oxygen generation, as well as on Earth. And electrolysis is one of the most renewable forms of hydrogen production, especially when that electricity comes from renewable sources. So, why do we care about bubbles? Well, the voltage stack up you see here, the equilibrium, the activation, the concentration, and the ohmic voltages, of these four, three of them are influenced by bubble formation and activity. So, the activation over potential is an added voltage or an added inefficiency to the reaction added at the surface of the electrode by the formation of bubbles, reducing the availability of electroactive surface to the ions in the electrolyte. The concentration over potential is influenced by the bubbles obstructing the flow of ions in the vicinity of the electrode, and ohmic over potential is the presence of bubbles in the bulk electrolyte, since they are less conductive than the electrolyte itself. Here you can see that for the range of current densities of interest to us, shown on the x-axis, we're interested in 250 to 500 milliamps per centimeter squared. Bubble coverage on the y can be quite high, between 20 and 50%. And so you can imagine that this will dramatically impair the efficiency of our reaction. And so our objective for these processes is to evacuate bubbles as rapidly as possible, or the inverse of the Finding Nemo moment. So there are a variety of ways that this can be done. Two of the most common are forced convection, where the flow of the electrolyte is directed past the electrode surface to pull bubbles off, detaching them sooner, and thus reducing those overpotentials. Flow-through electrodes are emerging in research and applications. In a lattice structure so that the forced convection can occur more effectively. But those both require power, and so they are suboptimal for spaceflight applications where we want low power and low complexity, so a reduction in the number of moving components and components that can break. Surface engineering is an option. It's most commonly done with texturing or doping of the electrode surface. But the most effective approaches are those which induce micro or nanostructures in the electrodes. But those coatings are only effective for a matter of hundreds of hours currently. There are other approaches which require power, such as ultrasound, pulsed pressure and power, and supergravity in centrifuges, which can be very effective, but again, added power, added complexity, as well as some environmental hazards, such as the noise of ultrasounds. And then finally, the magnetohydrodynamic techniques rely on the inducing of a Lorentz force in the electrolyte by the presence of a magnetic field, thus accelerating the bubbles with the bulk electrolyte along the direction of the Lorentz force vector, which is the J cross B, J being the current density and B being the magnetic flux density fields. And ideally, we would be able to do this without requiring electromagnets. And if we can accomplish this effect with permanent magnets, then that presents a highly attractive, low power, essentially negligible power added to the system, solution for evacuating bubbles more rapidly. So here's what that looks like. On the left, you see an electrode with no magnets, and on the right, an electrode with magnets. In the left, the bubbles move under the influence of buoyancy force alone, whereas on the right, there are both buoyancy as well as magnetohydrodynamic forces. And as a result, the bubbles move to the right side, and this increases the efficiency of the reaction. So the questions for this study are, can we benefits from these magnetohydrodynamic approaches for essentially inducing a local forced convection without requiring the larger packaging, keeping the inter-electrode gap small. And in this small gap between electrodes is the turbulence induced by this Lorentz force enough to rapidly evacuate bubbles, and then can this solution be scaled with permanent magnets for a variety of applications? Here's the experimental setup. We have an electrode submerged and a pair of electrodes submerged in electrolyte. And without a magnet, you can see the bubbles are moving under the influence of buoyancy alone. In the magnetic case, we situate a magnetic array, and I will show the field lines of the array on the next slide behind the electrode. And as a result of the orientation alternating from magnet to magnet, some of the bubbles are under a Lorentz force which points up, some down. And you can imagine that there is vorticity induced in this flow field as a result of the alternating directions of the Lorentz force. The experimental matrix includes three different magnet sizes and electrodes which are sized to cover one entire wavelength of the magnetic array, which is to say four magnets in each case. There is a no magnet control for each size, a constant magnetic field across the three sizes, as you can see in the equivalent B field, and then uh, to compare the highest B field possible given the experimental setup. So here's what the magnetic flux density field of this Halbach array, as it's called, looks like. The Halbach array is characterized by a sinusoidally varying orientation of the magnetic poles. Here you can see that array is discretized into four magnet wavelengths with the up, left, down, right pattern. And you'll notice that the field is concentrated on one side of the array uh, with this higher B field here, whereas on the other side, it's essentially negligible. It's canceled out. There's very little flux that escapes to the bottom side of the array. The electrode is shown here in green, and this is as close as the electrode can get given the experimental setup. And you'll notice that some of the vectors are pointing out of the array, some to the right, left, and down. And the effect that that has is when orienting a current density field with the electrode pointing up, with the field pointing upward, you'll notice that some of the Lorentz force vectors are pointing out of the page and some into the page. And so, for example, you can see that there's a vorticity vector which would be pointed upward here, which has the effect of swirling the flow. And our question is, can this evacuate bubbles faster? And just for comparison, you'll see that for the larger magnet size, the field lines are essentially the same, but the electrode is 4 times the size, and there are two positions. The green position being the equivalent magnetic flux density at the surface of the electrode as in the smaller case, in order to test the difference in effect of the spatial wavelengths of the magnetic array, as well as the closest position possible for this magnet size. So here's what the magnetic arrays look like. You'll notice the cells here, 3D printed resin to contain the electrodes on their backers. And the magnet arrays are situated just behind the electrode cells. Here's what the setup looks like. We have a potassium hydroxide electrolyte, which is common for commercial electrolyzers and for hydrogen, as well as in alkaline oxygen generating electrolyzers for spaceflight. The electrodes are here with a constant electrode gap across all magnet sizes. And there's a spacer that is included between the electrode cell and the magnetic array for maintaining that constant B field across sizes. So here's what the results look like. And right off the bat, we see that as expected, the cell voltage increases with current density. But unfortunately, if you zoom in on the 1/2 inch magnets from no magnet to equivalent magnetic field to the highest field possible, we see that there's an increase, which is not what we expect and is not what the literature on this topic um, shows. And so you'll notice that across all magnet sizes here, we have the flux, the various fluxes for each magnet size compared to their no magnet baselines. Only one of the magnetic configurations reduces the overpotential across all current densities. And so this is likely due to the presence of bubbles persisting in the bulk electrolyte, thus reducing the overall conductivity of the electrolyte and impairing the if reducing the efficiency of the reaction. In order to actually zoom in and understand a little bit what's going on in the cell on a smaller scale, electrochemical impedance spectroscopy is used to find out with an alternating current what frequency dependent processes are occurring in the cell. So essentially what's happening here is a suite of alternating current frequencies is taken, and from the data, an equivalent circuit model is fit so that the various processes here shown by the cabling, the ohmic losses, cathode, anode, and diffusion are represented by circuit elements which have the same dynamic response to that which we see in the cell. So the data sets for this can be a little hard to understand at first. We're looking at real and imaginary impedance plots here. But essentially, what's important to get out of this is the data points are the raw data from low to high frequency. Um, and the lines you see show that they fit the data quite well across all three sizes of magnets. So the takeaway here is that the data I'll show on the next slide well represents what dynamic response we're observing in the cell. So what is that response? Well, here you see that we are comparing the each magnet size and its various B fields to the no magnet controls. And we're trying to understand how do the individual components of the resistance in the cell compare across those different configurations. So we're interested in reducing resistance, obviously, and we have the normalized comparison. And you can see that there are some good effects and some detrimental effects. So ohmic resistance appears relatively unchanged. That could be due to the fact that some bubbles are traveling upward, some downward in the cell. And so particularly for the 1/2 inch magnetic arrays, the bubbles don't have anywhere to go. And so they have to travel back up past the electrolyte. And so it's likely that they don't have the space to evacuate quickly. And so that's not having an overall beneficial effect. We see some inverse behavior between anode and cathode. The array is closest to the cathode, so the B field is strongest there. And it could be that as bubbles are evacuated from the cathode, they impinge on the anode or vice versa. So it's possible that that's what we're observing. And then diffusion is dramatically reduced for the 1/2 inch, which is potentially due to the fact that the swirling that we see, or the vorticity inducing a higher local flow rate in the cell is increasing the availability of ions and water molecules to react at the electrode surfaces. And that could be reducing the diffusion resistance. In capacitances, and here the constant phase element Q, which is essentially an RC circuit, each for cathode, anode, and diffusion, we can extract capacitances from that combination of resistance and constant phase element. And we see increased capacitance in many cases. This is likely due to an increase in the available area of the electrodes to react evolving hydrogen or oxygen. So that's a positive result. Um, And overall, what we can take away is that some of these processes we're observing clearly show that the magnetohydrodynamic convection is having an effect in the cell and potentially designing the cell better to take advantage of those results would have a dramatically improved effect. One example of that would be rotating the magnets 90 degrees. As a result, the Lorentz force would accelerate the bubbles laterally, left, right, instead of up, down, so that the bubbles that are forced down wouldn't be traveling back past the electrodes. And that is what was done in this preliminary test case that I ran in a larger cell. So here we have not only bubbles that are swirling left, right, but also there's more space for them to be evacuated. And there was a very clear 18% benefit across voltage ranges for the cell. So that's something to investigate with a smaller gap. Controlling the buffer space on either side of the electrode would help control that parameter because that allows bubbles to evacuate past the electrode. And therefore, they have less influence on the ohmic loss in the cell with the larger gap here. Uh, and then lastly, a three electrode setup would allow for a reference electrode between anode and cathode, thus allowing us to extract electrochemical impedance spectroscopic measurements for both of them separately. And multiple interelectrode gaps might allow us to understand to what effect, potentially a slightly wider gap with a little bit of a higher ohmic loss would allow bubbles to escape faster, thus improving overall efficiency of the cell. So feel free to check out the paper on ResearchGate. It should be linked below. And thanks for your attention.